Our first application of the ideal gas law is when gases undergo a process called isothermal expansion or isothermal compression. Now, we'll see the term iso quite a bit here, so it's worth noting that iso just means same. So as our gas expands or contracts, something is staying the same in each one of these cases, and that will be what separates these different cases, is what's changing and what's staying constant. Thermal here refers to the temperature. So as our gas expands or contracts, its temperature stays the same. Now, if you've ever done something like pumping up a bike tire, you know that as you compress a gas, it gets warmer. You feel some heat there. And then if you've ever, say, used like an aerosol spray, so like Axe body spray, or like the canned air things used to spray out electronics to clean them, you know that when that gas expands, when it gets let out of its container, it cools off. So those are specific situations that would not apply to this isothermal thing. And the idea there is, well, it happens too quickly. So in an isothermal expansion or compression, typically we picture this as some gas contained in a container underneath a piston. And then in a compression, of course, the piston would be moving downwards. We have some work that's done on the gas, compressing that gas. Or in an expansion, that piston would be moved upwards, and the gas would be doing some work on the piston. But in either case here, we have to have fairly slow changes for it to be isothermal. And then we think of the whole chamber here as being connected to some amount of mass that's at a constant temperature. And so even if our temperature would tend to change a little bit as we, say, compressed this, that gas would tend to want to warm up a little bit, we have this whole chamber in contact with a large amount of air or water or steel or whatever the material is that's going to maintain a fairly constant temperature here. So as we build up some heat in here, that heat is going to transfer by conduction through the walls of the container into this material and bring this back down to its original temperature. So when that happens, when we have a situation like that, so this again is slow changes in contact with, we call this a thermal reservoir. It's just some large area with a bunch of capacity to take in heat or give off heat without changing the temperature of this thing significantly. But in an isothermal expansion, when we apply the ideal gas law, PV equals nRT, we need to identify what's changing and what's staying constant here. So both P and V could change in this case, but N, the number of moles, or the amount of the gas, that's going to stay constant. R, the ideal gas constant, always stays constant. And T is going to stay constant because this is an isothermal process. So for the case of isothermal expansion or compressions, we can just write out that PV is going to be equal to some constant value. Or we could write that as P1 V1 equals P2 V2. And so as this thing compresses, as our piston comes down, we can see that the volume would decrease. But to compensate for that, to make both sides of this equation equal to each other, our pressure would have to increase. So if we made a graph of this with pressure on the y-axis and volume on the x-axis, we'd see that as pressure increases, volume has to decrease, and as volume increases, pressure has to increase. This form of the equation might be useful to us. We can write this as pressure is equal to some constant value divided by V, divided by the volume. So this is just an inverse function, a 1 over function. So those in general have a shape something like this. Okay, and I guess I've drawn that a little bit too constant. There we go, something more like that. So as we go further to the right, volume is increasing and pressure is decreasing for this isothermal process.